Okay, so we have 2 more slides. Then after that, we stop our class. So we try to do the same thing, estimation of modified data that is incomplete data. Remember, chapter 1 is complete data, chapter 2 is incomplete data. That's why we have modified. How to modify? That is because of truncation and censored value. So based on this truncation and censored, that is we modify the data. It means that modify the data. So we have learned how to calculate the reset and apply to the Kaplan-Meier and also Nelson-Allen. And second 2.3 is the same thing applied to the Nelson-Allen or Kaplan-Meier, but different method. But this is only you have the observation. Okay, the observation entered at the beginning. That is the initial observation value. Okay, if you have the problem involve the initial observation at the beginning, then we have to use this method. You see how is it?
Let's go to other method to find the reset. That is reset with some observation entered at the beginning. Now consider a set of individual modality or loss of n data of a random variable x, which consists of the data of truncation, censored or uncensored values. As usual, the d is for the truncation value, u is for the censored value, and the y for the uncensored value. And x also the uncensored value, where the x is unique and also ascending. So the reset can be calculated at the ith order observation xi, which is given by this formula. This formula is different from the formula we have learned previously. So previously we have learned the reset value, which is equals to the conditional for the frequency of x plus the conditional for the frequency for u and minus the conditional frequency for the d. So this is a formula that we have learned before. And now we try to learn this formula, that is we try to take this minus these two. With the following conditions, this condition frequency of x is a number of x such that x is strictly less than xi. Previously our x is greater or equals to xi. And for the conditional frequency of u, that is the number of u's is strictly less than the xi. And for this conditional d as well, that the number of d's is always strictly less than xi.
Okay, you get it? Now, if the problem involve the observation at the beginning, so you can use this method to solve, or this method also same. Both also can solve. Okay, so I try to introduce another method. So for the second method, you have to do another round that is not this. Okay, you have to take this minus this. Okay, and the condition for this frequency is opposite. That is now is strictly less than. Previously is more or equal, right? Now is strictly less than. Okay, please take note. Carry on.
So if you consider the observation entered at the beginning, that is this, then you have to use this formula to count. So I will show the example later. Before we go further, let's look at the set of the truncation value, that's for d, the censored value for the u, and the uncensored value for the y and x as well. So let's say this is a set for the random variable x, and in this set we have set for truncation value, and we have another set that is for the censored value. We have a y, that is uncensored value. And inside this set y here, we may have another subset of y that consists of this x value. So it's the same as what we have learned previously, that this set of the random variable x here, perhaps we have truncation values, census value, and uncensored value. So let's go to example 9.
Okay, before go example 9, you have to understand this subset, right? Because this y is, the y value is uncensored, it may be repeated. Okay, so after you take out all the repeated value as a distinct, then become x. Okay, in fact, they're the same. Only this is distinct and repeated. This is repeated. Okay, so this one we have practiced many examples. Okay, now let's go to example 9.
Example 9. You are given the following regarding a 2-year mortality study. 10 lives enter the study at the beginning. So it means that this enter data, which is referred to the truncation, that means our truncation value is 0 at this frequency is 10 because we have 10 entered value at the beginning. That is 0. So the first data we have 0. Next, one additional life enter at each of the following times at 0.8 and 1.0. And this also refers to ender, that means it's a truncation value. So here we have 3 truncation value. And next, one life terminate at time 1.5. Terminate definitely is referred to the censored value. So at this time 1.5, we have one censored value, that's u. So we move to next. One death occurs at each of the following times. That means 0.2, 0.5, 1.3, 1.7. These 4 data are referred to the uncensored value because of death. So this you can name as the y values. So from this raw data here, you need to rearrange in ascending form. So that means we have 0, next is 0.2, and next is 0.5, 0.8, 1.0, 1.3, 1.5, and 1.7. So obviously this is D. These 2 are the Y values, and 0.8 and 1.0 are the truncation value. 1.3 is Y value, 1.5 is U value, and 1.7 is Y value as well. Our purpose is to find the product limit estimate of this survival at 2. This product limit means that we have to use the Kaplan-Meier to estimate the survival at 2. So remember, all the data here are referred to time. So the time is 0 means that at the beginning. Let's go to the solution of example 9. Let x be the random variable representing the mortality data of time. So y is represent the uncensored value, u represent the censored value, and the d represent the truncated value. Next, I need to plug all this ascending value inside this table. Please note that this nyj is a number of observation of yj, nuj is a number of observation of uj, and this ndj is a number of observation of dj. So we plug the first value that is here, and the second 0.2, 0.5 is for the y value that is here, 0.2, 0.5, and the next value will be 0.8 and 1.0. That is for the d again. So this is a 0.8 and 1.0. And next will be y again, that is 1.3. And next will be 1.5, that is u here. And the last one will be 1.7, that is belongs to y. So according to questions, the depth value occurs at each of the following. That means the number of observations of this depth value all are 1. And for the censored value, there's only 1. At the beginning, that is when d is 0, we have the frequency which is 10. We have 10 times. And the rest for this truncation value is 1 for each. So we have completed the table, and now we can proceed to next. See? So let's place the x value. So the y value we have found just now, that is this, 4 values, all are distinct. So in this case, the y value actually is equals to x value as well. That means now my x value is 0.2, 0.5, 1.3, and 1.7. So please take note, this xi actually is equals to yi as well. So the number of frequency we have found just now, which is 1, 1, 1, 1. Now I would like to count this conditional frequency. So if I choose my x1, which is equals to 0.2, how many x value is less than 0.2? There's no x value which is less than 0.2. So if I choose my x2, which is equals to 0.5, then how many x value which is really less than 0.5? We only got one value which is less than 0.5. So similarly, if I choose my x3 is 1.3, so how many x value is really less than 1.3? We have 2. And of course, we have 3 value which is less than 1.7. So the u value we have just now is 1.5. So how many u's value is less than 0.2? We do not have any value less than 0.2, that is 0. So again, how many u's value is less than 0.5? I have nothing. So similarly, how many u's value less than 1.3? Also nothing. And the last one is how many u's value which is really less than 1.7? I have 1. So now we go to the d, the truncation value. The d we have just now was 0 and 0.8 and 1.0. So remember, this one we have 10 units, this one we have 1, this one we have 1. So now how many d's value which is slightly less than 0.2? I have 10 0 which is less than 0.2. So how many d's value which is really less than 0.5? I have 10 0 which is less than 0.5. Now, how many d's value less than 1.3? I have altogether 12 values which is slightly less than 1.3. And the last, how many d's value which is less than 1.7? Again, I have 12 values which is slightly less than 1.7. So next I can calculate the reset value, that I'm going to take this column minus these 2 columns. So we will have 10, 9, 10, and 8. And now I can solve the problem. So the problem actually is asked to find what is the survival at 2 by using the Kaplan-Meier. So we know that 2 is inside this range, that the last range will be 1.7 to infinity. So since our 2 inside this range, then in order to count the survival at 2, actually it's the same as survival at the lower bound, that is at 1.7. That means we have to consider this row, that you have to consider all the reset value. So for the Kaplan-Meier, the formula is 1 minus the number of x divided by the reset value. So we will have take 1 over 10 times 1 minus 1 over 9 times 1 minus 1 over 10 times 1 minus 1 over 8. Simplify this, you will have 9 over 10, 8 over 9, 9 over 10, and 7 over 8. So you can see that this is recancelled, and left 63 over 100.
Okay, good explanation. I think very clear from this video clip. Okay, only here I want to highlight that is okay, this diagram. So when you try to fill up this diagram, make sure that your here, okay, this is important. That is, you have to know what is your truncation, censored and uncensored. After that, you have to rearrange for in ascending form. Okay, so once you have this already, now you have to place the table. So when you place the table, you also must be careful. There's no overlapping. Okay, so you can see that this is the frequency. N is referred to frequency. The data is come from the Y, U, and D. So when you place, there's no overlapping. So this first row is occupied by the 0. And then after that, there's no data for the Y and U at all. Okay, so like for example, this 1.3 occupied by Y, then U and D, there's no more data. You have to know that there's no overlapping. Okay, so do you need to plot this table? That's up to you, because the most important is this table. Okay, the most important in this table, once you have completed this table, then you can solve the problem. Okay, so if you can see without draw the first table, you can straight away jump to here, no problem. You can go ahead. Okay, so as I told you in my tutorial solution, some of the solution I only use one table. Okay, now I think it's quite clear for this example. Okay, now remember class for this problem, you have to understand that enter at beginning, okay, definitely your D is 0. This is a truncation. Enter is referred to the truncation. Terminate, surrender, all these are referred to the U. Okay, definitely is referred to the uncensored value. That is either is X or Y. Okay, so we have to take note. Okay, so for this example done, let's move to the next example. Okay, so this is the last one for today lecture.
Example 10. You are given the following data from a clinical study as follows. So given the data in time, based on the event, we have 20 new entrants, that this is referred to the truncation value. So we have 20. The end of the frequency of this triangulation is one depth value, which is referred to y. 9 termination is referred to the censored value, and this is uncensored, y is uncensored, and the frequency of this u, which is 9, and one depth that is uncensored for y, one new entrance that is d, one depth y again, one termination that is u, and two depth also refer to y, and this we have frequency of 2.
Okay, class, before we go further, if you look at this table, do you know where is our data? Our data is here. Time is our data. This is just a frequency. Okay, 0 is a data. We have 20 data of 0. We have 1 data of 1.1. This is our data. This time is our data. So this time can be referred to minutes, months, or year. We do not know. Okay, just as a time. It's a data, please. Okay, carry on.
So based on this data and also the frequency here, that we need to calculate the absolute difference between the product limit of S6 and the Nelson-Allen estimate of S6. So our aim for this problem, that is, we try to find the absolute value of this difference, that is S6 under Kaplan-Meier, let's say is K, and minus this S6, and based on the Nelson-Allen, let's say is Sn. So this is our aim. So let's look at the solution of this example 10. Let X be the random variable representing the mortality data of time from a clinical study. So we define the following, that the xi is an uncensored value, u is the censored value, and the d is the truncation value, and xi is a number of xi, and these three are the conditional frequency for x, u, and d respectively. And of course our Ri is a reset value. So I'm going to try to plug all this value to the table. Now for this example 10, I'm going to use only one table, which is different from the method we have used before. That means I'm not going to consider the y, I straight away to consider the x. Our uncensored value.
Okay, so you please pay attention. Now I just use one table. Okay, instead of using two tables. Okay, so you have to take note because you may confuse. Okay, so one table you may confuse. Please pay attention.
We have here y, 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 y. So that means all these are my x value. All the data here you can see that is ascending form. That means you no need to rearrange. And now we try to put all the value inside this table. You will have this. So at first I have 0 for the truncation, and next I have 1.1, and next I will have 1.5 for the censored value, and next will be 2.3 for the uncensored value, and next will be the 3, that is for the truncation value, and next will be the 3.2 for the uncensored value, and next will be the censored value, that's a 4.7, and the last will be the 6.0, that belongs to the uncensored value.
Okay, first of all, this data do not place wrongly. Okay, the data must according ascending form. Okay, if you go down, like you can see 0, 1.1, 1.5, 2.3 is ascending form. Okay, please, if you upside down, then you got problem. Carry on.
Next, we try to place all the frequencies of this data. So for the uncensored value here, we have 1, 1, 1, 2. And for this 1.5, from the censored value, we have 9. And 4.7, we have 1. Now, under truncated value here, for this beginning data, we have 20. And for this trait, we have 1. And next, we try to calculate the conditional frequency of X, U, and D respectively.
Okay, class, before go further, please do not confuse the notation. So this NXI and this NXI is different. Okay? So I hope you understand. This is a frequency of Xi. This is a conditional frequency. And here is the same. This NUI and this NUI is different. This is a frequency of UI. Okay? This is a conditional frequency of the U, which is less than the Xi. Okay? Please do not mix up this frequency and this frequency. Okay? Carry on.
So you have to take note here, because I'm using only one table, then you only look at the row which consists of this uncensored value. In other words, we are looking for these 4 rows.
This is important, class, because under one table here, you cannot find all the R value in all the row here. There's only 4 rows that you need to consider based on the uncensored value. Okay, so uncensored value, we have four values here: 1.1, 2.3, 3.2, and 6.0. So you only refer to the row for 1.1, 2.3, 3.2, and 6.0. That is this. Okay, the rest here, there's no R value. Only this you have R value. This is important because you're using one table only.
So look at the first condition here. I'm going to choose my first X value, which is 1.1. So how many X value which is less than 1.1? So I don't have any X value which is really less than 1.1. So here I got 0. Do not put here. And next, I'm going to choose my X value is 2.3. So how many X values which is really less than 2.3? So I only have one value of 1.1, which is less than 2.3. So here is 1. And next, I'm going to choose 3.2. So how many X value which is really less than 3.2? So I have 2 values which is really less than 3.2. And the last one is I'm going to choose my X is 6.0. So how many X value which is less than 6.0? So I have 3 values which is less than 6.0. So here is 3. You please take note here, don't write anything in this column. So that means this should be nothing in this column. Do not fill anything in this column. Next, I'm going to consider this second condition. Repeat again, I choose my first value of X is 1.1. So how many use value which is less than 1.1? We don't have any use values which is less than 1.1. So here is 0. And next, I'm going to choose my X value is 2.3. So how many use value which is less than 2.3? I have 9 of 1.5 which is less than 2.3. So this is 9. Next, I'm going to choose my X value is 3.2. So how many use value which is less than 3.2? Again, I have 9 values of 1.5 which is less than 3.2. So here is 9 again. And the last one is I'm going to choose my X value which is 6.0. So how many use value which is less than 6.0? So all these U values which is less than 6.0, that is I have 10 of use value which is less than 6.0. So this is 10. So similarly for this condition of B, So the first value, I'm going to choose a 1.1. So how many D's value which is less than 1.1? So I have a 20 of 0 which is less than 1.1. And the second X value I'm going to choose is 2.3. So how many D's values which is less than 2.3? Again, I have a 20 of 0 which is less than 2.3. And the third one, I'm going to choose my X value is 3.2. So how many D's value is less than 3.2? So these values are less than 3.2. That means I have a 21 of this value which is less than 3.2. So the last one is I'm going to choose my X is 6.0. So how many D's value which is less than 6.0? So again, it's a 21 of this value are less than 6.0. So now I'm going to calculate this R set value where the formula is equals to frequency for the D minus the conditional frequency for the X minus the conditional frequency for the U. So do not use a wrong formula, because this example we are trying to consider the data entered at the beginning. So that means you have to do reverse by taking this formula. In other words, we have to take this minus these two columns to get the R. So this minus this will be 20, and this become 10, and this become 10, and this is 8. Our aim of this problem that is to find the absolute between the survival at 6 based on the Kaplan layer and the survival at 6 based on the Nelson-Allen. So that means we have to find this one from Kaplan layer. Since our 6 is inside this group, that is the 6 is in the last group, that is from 6 to infinity. It means that we have to consider until the last row. That means you have to consider all the R value. So our survival at 6 under Kaplan layer, that equals to 1 minus 1 divided by this R, that is 1 over 20. So that's the reason I told you just now, do not place in the wrong row. You may get the wrong frequency or you may get the wrong reset value. So, and multiply, the next will be 1 minus 1 divided by 10 times 1 minus 1 divided by 10 and times 1 minus 2 divided by 8. You will have 4617 divided by 8000. And next I'm trying to use the Nelson-Allen to count. Now we know that the Nelson-Allen is to calculate the cumulative hazard rate instead of survival. So let's calculate the cumulative hazard rate at 6 by using Nelson-Allen. So this Nelson-Allen, again, we have to consider all the risk value here. That means now we have 1 over 20 plus 1 over 10 plus 1 over 10 and plus 2 over 8. This is equals to half. And therefore, we can find the survival at 6 under this Nelson-Allen, which is equals to exponential to the power of negative half. So therefore, this absolute difference between the Kaplan layer and the survival under this Nelson at 6, which will equal to this value minus this. And you will have about 0.0294. So please take note here, some students may take this survival as 6 under Nelson-Allen minus this survival as 6 under Kaplan-Meier. You may get the same result because after absolute will become positive.
Okay, very good explanation and very clear. Okay, so this is under one table, so I already explained quite detailed. Okay, now you before you go, actually you can try the example 8. Remember just now the example 8 we use the first method, and the example 8 actually is let me show you. I don't know which slide. Let's just try. Not this. Not this. Okay. Yes, this example. Okay, so if you look at this example 8, we use the first method to solve this problem. Okay, so we do not consider this method is we do not consider the first entered value. Okay, so we use the first formula. Now, but this example 8, you can use this just now the second method to solve. You can try yourself, you get the same answer. Okay, that means at the beginning we have n life. That's a d truncation is 0. Okay, for these questions. Okay, so you can try yourself. If you want to practice, you go ahead. You will get the same answer with a different method. Okay. So, any question, class? Thank you, Kan Ziyang. So, if you have no question, you may go now. I have finished everything for today's lecture. And next, this one we have one more section. So next week I will continue. Okay, for the third portion of this chapter 2. That is from the discrete, we can change to the continuous under this triangular. Okay, you will learn next week. No worry. Okay. Okay, that's it. If no, I see you. Okay, later. Okay, next week. Thanks.